Okay, welcome everyone to today's seminar. Today we're very happy to have Edgar Shaghoulian from Cornell, who's going to tell us about islands and asymptotically flat 2D gravity. Edgar, please take it away.
Thank you, Ignacio. Thanks for being here. As Ignacio said, I'm talking about mostly this paper that appeared a few months ago with Tom Hartman and Andy Strominger. Let me see if I can turn on my... Yeah, I guess you should see a laser pointer, hopefully. I'll start off by briefly kind of very quickly reviewing some results from this paper that appeared last fall. This is the 1911 paper. And for people who don't know the background of these things, I suggest a sort of review paper that we wrote with the same authors about a month ago. It starts off sounding pretty basic because we reviewed general relativity and things like that. But if you go deeper into it, I think there's sort of some useful stuff for everybody. So just want to advertise the review for people trying to learn what's going on in this subject. I'm not very good at paying attention to the chat, so if you have questions, please unmute yourself and ask away. So let's get started. So a quick history slide to contextualize something I'm sure everybody already knows. In 1976, Hawking very famously computed the entropy of his radiation, Hawking radiation, and found that it was thermal. So in the context of black hole creation and evaporation, he seemed to find that pure states evolve into mixed states. So here's a plot in green of what Hawking's calculation for the entropy of outgoing radiation looks like. It just kind of increases in time until the black hole completely evaporates away, and then it's just some large finite value. That's not good because that seems to violate unitarity of black hole evaporation. In 1993, Don Page provided a target for what the entropy of radiation should look like. He assumed that the end state is pure and computed what we call the Page curve, which agrees with Hawking's curve. It goes, up at the beginning of the evaporation process. There's some sharp turnaround, and then it follows the thermodynamic entropy of the black hole and goes back down to zero. So this was Page's target of what the entropy of radiation should look like if the theory of gravity you're considering is unitary. And there was a flurry of progress last year. People computed first the Page curve from a holographic setup using Ryu-Takayanagi and its extensions. And then there was a derivation of the Page curve using the gravitational path integral. This is in simple 2D models of gravity that I'll discuss in a second. And it sort of used the crutch of anti-de Sitter space. And that's the thing we're going to try and improve on a little bit in this talk, which brings me to the next point. How does this stuff work in flat space? Does it work in flat space? That's what we want to talk about today. But before I get to that, I want to discuss quickly this the sort of work from last year. All right, it's going to be a pretty lightning review just to flash some kind of cartoons and slogans. So the model that was considered in many of these papers is JT gravity in ADS2 plus a large C CFT. So here's the strip. This is ADS2. It has two boundaries. And there's a gravitational action, which I'm not going to write down because I'm not going to need it. Like I said, I just want to flash some pictures, plus a CFT action. It's important that the CFT is only coupled to the metric, not the dilaton, which is a piece in the gravitational action. Okay, the dilaton is there to make the gravitational action non-trivial. So the theory looked something like this. And an important step was that the title slide is gravity coupled to CFT with wings. There are these bath regions, these flat space regions that are appended to the ADS2 diagram, where you have the same large C CFT, but you don't have gravity. So in particular, you give your two-dimensional CFT transparent boundary conditions across this ADS boundary. So if there's Hawking radiation or any null particle that comes to this boundary, it just goes right through into the asymptotically flat region. And you do it to both sides. Okay, this is not a crazy thing to do to shut off gravity here, because in the solutions that we care about, the dilaton is diverging near the boundary. And in these 2D models, the dilaton is setting the strength of the gravitational coupling. So gravity is getting weak near the boundary, and then you leave it shut off out here. Okay, that still even though it's motivated, is a little uncomfortable to do this gluing. When you do when you try and derive various things, you need to face all sorts of knowing technical complications, and it's not clear that this is a, you know, from a top-down point of view, that this is a totally reasonable setup, which is one of the reasons why we'd like to extend it to just asymptotically flat space without this kind of gluing, just to make sure that everything works as it should. So this was the model that people considered. And how do you see in this model the page curve of Hawking radiation? Well, like I said, I'm just going to flash some pictures. What we want to do is we want to use the replica trick to compute the entropy of Hawking radiation. So here I've represented the replica manifold for the second Renyi. So this is a Euclidean calculation. So this first sheet here, ignore the second sheet for now, this first sheet here is the Euclidean version of the space-time that I've drawn here. Okay, the ADS2 region is supposed to be what's inside this circle, and the flat space region is everything out here. So that's how we wanted to compute the entropy on the union of this interval and this interval. Okay, the way you do that is you compute the nth Renyi. Here I've represented a second Renyi, so you make a second copy and you glue together these two sheets across the cuts. Okay, so this is how the replica trick in field theory looks like. You compute the partition function on this topologically non-trivial manifold. But here we want to do a gravitational path integral, okay? We want to compute the entropy of radiation in a theory that has gravity, at least in part of the space-time. What that means is you fix the boundary conditions here, and then you do the gravitational path integral inside. So you fix the boundary conditions here and here, and then you just have to do the gravitational path integral. Okay, that's how we understand gravitational path integrals. So in particular, one thing you can do is just to fill in with the hyperbolic disk with ADS2 independently on each region. Okay, this is the calculation that would give you something analogous to Hawking's answer for the Hawking radiation. You would find that it just increases linearly in time. But if you're doing the gravitational path integral and you believe they should sum over all geometries and topologies, there's a very natural other thing to do, which is to connect these two via a wormhole. Okay, you need to check, given your particular theory, whether this is actually a solution to the equations of motion, but such a thing should exist, you know, at least as an off-shelf configuration. In particular, computing the nth Renyi, you can see that you can sort of connect up all the sheets in this way, and you can do various other things, connect up a few of these sheets and not the other ones. You know, there's a large number of things you can do at any given n. And the punchline of the work from last fall is that it's these configurations, these replica wormholes that connect every sheet to every other sheet, which give you the dominant saddle in the latter part of the page curve where the entropy of the radiation is going down. Okay, so this is how you see from the gravitational path integral how to get the unitary answer for the entropy of Hawking radiation. Now, this doesn't give you the density matrix of Hawking radiation. This is something that people have been talking about a lot in the past several months. All it really seems to tell you is trace rho log rho for the exact density matrix rho. Okay, and we would really like access to the exact density matrix rho, but we don't quite yet know how to do that. And it's believed that you can't do that by these semiclassical Euclidean gravity techniques. Okay, I'm not going to talk much more about replica wormholes. I mainly set this up to show you that this gives you, this perspective gives you what's called the island rule. Okay, so you compute these Renyi entropies, and you want to compute the entanglement entropy in the end, which means you want to do an analytic continuation to n equals 1. And so you might think, well, these wormholes are finite n things. What role do they have at n near 1? Well, they leave an imprint. Because of the non-trivial analytic continuation, they can leave an imprint. And the imprint they leave is precisely the island rule for the entropy of radiation. Okay, this was proposed by several authors last year by thinking about holography and what holography would tell you the formula is. And it tells you the entropy of radiation, the von Neumann entropy, is given by first doing an extremization over what are called island regions I. And you do an extremization of what's the generalized, what's known as the generalized entropy. So there's the gravitational entropy of region I, which is, you know, we're used to as A over 4G, but if you have a different theory of gravity, it's a different expression. And you add to that what I like to call the semiclassical entropy on R union I. The semiclassical entropy means this is like the Hawking style entropy. It's the entropy of quantum fields on a fixed gravitational spacetime. Okay, so this is just a Borel-Davies QFT and curved spacetime type of computation. So you add those two things together and you extremize over island regions I, which can be disconnected if you want. And if there are several island regions I, you take the minimum over all of them. So if you go through carefully, at least in the 2D JT model coupled to flat space or other variations of the JT model, you'll find that this is the formula that comes out of doing the replica calculation carefully. And we can see from this formula how we get a unitary page curve. So in this context, we're talking about the eternal black hole. Okay, I'm not going to do an evaporating black hole just because that's, well, that hasn't really been done from the replica point of view. It should be possible, but it hasn't been done. But for the eternal black hole, here I've drawn the Hawking modes. So blue is entangled with blue and green is entangled with green. And let's say we're computing the entropy of radiation on a piece here on the left asymptotic region, union a piece here on the right asymptotic region. And we consider the evolution of that in time as we evolve time forward on both sides. Okay, there's a time evolution killing vector in the space-time, which requires evolving time forward on one side and backward on the other side. If we did that, since it's a symmetry, the entropy would not change, but we're evolving time forward on both sides. So the entropy can be non-trivial with respect to this evolution. And we see that at an early time, okay, this green mode is captured by this slice and its partner mode is captured by this slice. So we don't get any entropy from that pair of modes. And the blue mode is missed by this slice and it's also missed by this slice. So we don't get any entropy from that mode. But we see as we evolve to a later time, this green mode, which was captured here, is no longer captured by this slice, while this green mode that was captured by the earlier slice is still captured by this later slice. So if you think about it as some bell pair, that contributes log 2 worth of entanglement. And a similar thing happens with the blue mode. It's missed by both the earlier and late slice, but it's caught by the late slice on the right side. So we get another log 2 from this piece. This is just a quick cartoon to see that the entropy should increase in time. You could compute exactly in this model because it's just a 2D CFT on a fixed background spacetime, so we know what the formula is, but these pictures are sort of useful to see how the entropy changes as a function of time, and this picture shows you that it increases as a function of time. And it also quickly shows you how the island fixes that. If we now insert an island region, we see that the entropy of radiation has this piece in it, this semiclassical entropy of R union I. And now we see that while the green mode was missed by the later right slice, it is caught by the island. So the entropy doesn't go up due to the green entangled pair. And a similar thing with the blue mode. While the blue mode is captured by the later right slice, it's also captured by the island. So inserting an island here in this way is what keeps the entropy from going up and up forever. And the analog of the page curve in the eternal black hole is something that looks like this. It follows Hawking's curve at the beginning, but then it saturates at 2 times the black hole entropy, 2 times because there are 2 black holes here, the black hole on the left and the black hole on the right. Whereas the Hawking answer would have increased linearly in time forever. The black hole never evaporates away, so it just keeps producing more and more entropy. Okay, so this is what the replica wormholes give you. Any questions about that?
Yes, there is a question in the chat. Okay, it's a bit long, but I'm going to read it anyway. So from Nehal. So could you comment on what the branch cuts in the previous slide signify physically? In particular, if I am not wrong, in the CFT, for example, Calabrese-Cardi replica calculations, the partition function of an n-copy system with 1 branch cut is the same as the partition function on the torus. So is it that by this replica trick, you are calculating the higher topology perturbations? If so, do you expect higher order corrections too?
So the branch cuts here are exactly the same as the Cardi-Calabrese branch cuts. So it's really the exact same thing that you would do. So this is in Cardi-Calabrese language, this would be how you'd compute. Well, since this goes off to infinity, if we ignore this gravitational region, this is how you'd compute a single interval entanglement entropy. Instead of putting these branch cuts all the way out here, I could take the complement and have the branch cut go across here. And this would be, again, if I ignore gravity, identical to like a single interval in field theory entanglement entropy computation. The difference here is that when you get to the step of computing the partition function on this non-trivial manifold with these cuts that go across, you need to do this gravitational path integral. Now, when you go into the details, it turns out to be useful to represent manifolds like this as like additional branch cuts that go across here. The reason is, what these branch cuts tell you, they tell you as you go on this sheet through this branch cut, you come out down here. And what does a wormhole do? Well, it's similar. As you go in through here, you come out down here. There's an important difference, which is on this replica manifold, these points at the end of these branch cuts, they're singular, okay? They're these singular points at the end of these branch cuts. But this thing here, this wormhole is supposed to be smooth on the replica manifold. Now, when you go to the quotient spacetime, it sort of reverses. If you take a quotient of this smooth thing, then there are going to be singular points on the quotient spacetime. Whereas these branch cuts are going to sort of be smooth at their points on the quotient spacetime. So drawing these wormholes is pretty similar to drawing a branch cut, except you need to remember where the singularities are on the replica manifold versus the quotient manifold. But I'm not going to, I think, spend much time on the replica perspective, so I'll leave it at that. And if at the end there are more questions, I can entertain them then. Any other questions about the island picture? Okay, well, this is going to be sort of our premise as we move forward. And like I said, we want to consider a situation where we're just asymptotically flat. We don't want to do this gluing of ADS to flat, just because we want to make sure things are kosher. So let's move on to the flat space setup. So the model I'm going to consider is the CGHS model or the RST model. And I'm going to spend a fair amount of time on the background of the model because I think many people aren't really familiar with it. And once the background of things are set up, the computations are relatively straightforward. So I'll just sort of quickly flash what the answers look like. And there aren't really going to be very many, well, in my opinion, there aren't really any surprises. But you have to be a little bit careful in the computations. So why did I write CGHS/RST model? Well, they're very closely related. The CGHS model is this piece of the action here. Okay, there's a dilaton that enters exponentially. And you have a Ricci curvature term, you have a kinetic term, and you have a cosmological constant term. And then you have some CFT action. Okay, in the original literature, this was often considered to be n-free bosons. But here I'll just assume it's some large C CFT. I won't really specify until various points. And the RST model just adds this term. Okay, and I'll say in a second why RST added this term. But this is the classical action. And there's a conformal anomaly, right? The trace of stress tensor is proportional to the Ricci scalar, which you can integrate up in a covariant way to put into the action like this, R1 over box R, okay, with this particular coefficient. So the full action is the sum of these two things. And this is, this is supposed to be thought of as like the one loop effective action, but at large C, this full action is exact. Okay, it gives you the correct answers at leading order in C. And in fact, it's equivalent just by some field redefinitions to what's sometimes called flat space JT. Flat space JT has an action that looks like this. This dilaton here is different than this dilaton. It's basically e to the minus 2 little phi. And it has this cosmological constant piece, which normally you think might be true. It's just a cosmological constant, but it's important. It changes the equation of motion of the metric, which is thought of as an equation of motion for the dilaton. So just by some field redefinitions, you can put this action into this form. And the thing I want to point out is the CGHS action, meaning without this term, if you added this anomaly piece, it would not be equivalent to this action here. Okay, it's important to have put in this RST term here, and then this full action including the anomaly plus the classical piece, is equivalent to this. Or another way to say is just the pure classical CGHS action without the anomaly term is equivalent to this. Okay, we'll come back to that in a second. One thing we want to do to this model is we want to restrict the range of the dilaton. I'm not really going to use this flat space picture very much. I just wanted to flash it here so people get some intuition in case they're more familiar with this model, that they're really very similar. So something we want to do to the CGHS or RST model is restrict the range of the dilaton. That's because, I mean, these dilaton gravity models, as always, are thought of as models of higher dimensional gravity. In higher dimensional gravity, the dilaton is related to the size of the transverse sphere. And we don't want that to become negative. That doesn't really make any sense. So you give it some cutoff, okay? And if it goes, below this point, that's interpreted as like a singular point of the space-time, because that's when the sphere sort of shrinks, like at a singularity in higher dimensions. So singular points would be denoted by phi equals phi c. And if we take this model, we're in 2D. So what one should almost always do in 2D is work in conformal gauge. We see that the appropriate physical variables seem to be just this dilaton phi and this conformal mode rho. Okay, those are the two physical fields of the problem. The CFT here just sits here to provide a stress tensor for the equations of motion. So it provides a semi-classical stress tensor, and that's basically its role in life. Okay. Now, one thing I want to point out, one last thing about the relation of this flat space JT model to the CGHS RST model is that the CGHS model has a U1 current, which is d mu rho minus phi. But that current is broken by this anomaly piece, okay? And historically, the reason RST introduced this term was because they wanted to restore this U1 current. They wanted that to still be preserved because it helps in writing down exact solutions and solving the model carefully. And that's really why they added this term. And via this equivalence of flat space JT, you can sort of see that happening. This U1 current given by d mu rho minus phi, it's equivalent to the shift symmetry in this dilaton phi. So if you have the shift symmetry, you'd better have a U1 current. And so this model can only be dual to the full RST plus anomaly term and not the CGHS plus anomaly term, because that one doesn't have a U1 current, okay? That's a quick background of the model we're going to talk about. When we get to black holes, we're going to consider black holes of large mass. And when we consider black holes of large mass, this term plays a subleading effect. So really, you could have considered either model. So I'm not really going to distinguish between the two once we get to black holes.
So as a classical theory, you can do anything you want. But if you're going to quantize the theory, how do you enforce phi greater than phi c? And the field does whatever it wants.
Yeah, no, I don't think, well, there are various proposals of what to do with that point. And I don't think, yeah, I don't think in the early literature that was ever really understood, that point. I mean, it was interpreted, well, let me get to some solutions in a second, and then we can maybe revisit the question there, because there are various interpretations people made along the way, and I don't think that point was really well understood. So I basically agree with you, but it's yeah, that point I think is still a little mysterious.
Yeah, it was related to the fact that back at the time they didn't see any way that the Hawking radiation would shut off, and so you ended up sort of evolving towards a naked singularity. Yeah, and that just was the endpoint of well, it was one of the reasons people sort of got disgusted with the model.
Yeah. That was one of the things that I was going to comment on briefly, but mostly sweep under the rug. But I'll mention it now since you brought it up when we get to it. What Emma was saying is that another reason to think about this is, well, okay, we'll get to it in a second. I'll comment on another reason why people wanted to enforce this inequality in a moment. Okay, this is the model that we're going to consider. All right, let's talk about some of the solutions. One thing that's quite amazing about this model which I mean, I didn't know much about this model until I started working on it, is the equations of motion are trivial. I mean, you can solve it for basically general stress tensor source. So you can make some field redefinitions and gauge fix further so that you only have one field, which is conventionally called capital omega. In general, it's some combination of rho and phi, okay? And, or you have two fields, which you can think of some combinations of rho and phi, and you gauge fix, and then you just get one field omega, which is some combination of phi, some function of phi. So it's some scalar field. And in this particular gauge, which is sometimes called Kruskal gauge, you have this equation, which is like the equation of motion, and then you have these, which are like the constraint equations. Okay, what I mean by T flat is that it's the stress tensor, not in this metric with the e to the 2 rho, but just in this metric, the flat metric, dx plus, dx minus. So in particular, without the anomaly that comes from the conformal mode rho. Okay, it's just a simpler way to write the equation of motion. And you can just integrate this up to get the general solution for arbitrary T flat. And the restriction I was talking about before of keeping phi greater than or equal to phi critical for some critical amount, here we'll, in convention where that's equal to 1/4. So omega has to be greater than or equal to 1/4. Okay, and omega equals 1/4 will signify singularities in the space-time. All right, well, the first solution is what's called the linear dilaton vacuum. Okay, omega takes this form. And like I said, these equations are simple enough. You can, for example, quickly check this one and see that it's true, that derivative is -1. The metric, if I wanted to go back to what the conformal mode rho looks like, is like this. And I can define these flat coordinates sigma, which are, you know, x plus is just e to the sigma plus, and x minus is minus e to the minus sigma minus, and you get a flat metric that looks like this. The stress tensor in the x coordinates, like I said, is given by the flat piece plus the conformal anomaly coming from rho. And this tells you that the stress tensor in x coordinates or in sigma coordinates is equal to 0. Okay, that's why it's called the vacuum, because for an asymptotic observer who's inertial with respect to these coordinates, they see 0 stress tensor. And this, you know, sources this omega. Okay, you could say, why is this called a linear? There's nothing linear here. There's no dilaton here. But if you go back to the phi field and write its solution in terms of sigma coordinates, it's linear in the sigma coordinates. Okay, that's why it's called the linear dilaton vacuum. But in terms of the omega field, it looks like this. Here I've drawn what is, you know, the ordinary, so the 2D Penrose diagram for flat space, you can sort of unfold it, and it's this full diamond. And omega equals 1/4 is this time-like curve that sits here. And this is one of the steps where, you know, authors made an interpretation for what the singular point would mean. Normally, you'd be quite troubled by this. This looks like a naked time-like singularity. But when this omega equals 1/4 line was time-like, it was interpreted as something you just put reflecting boundary conditions on. So if something comes here, you just reflect it back inward. And the reason for that is, you know, spheres shrinking to 0 size along a time-like curve, if you think about in higher dimensions, can be thought of as just the origin and polar coordinates. So the origin and polar coordinates, if you send in an S wave, it's just going to kind of reflect and go back up. So that's why people imposed reflecting boundary conditions. That was a choice, okay, to analyze the model. All right, so that's thought of as the vacuum of the theory. Let's go to a slightly richer solution, the eternal black hole. Okay, omega still has a very simple form. It's this combination. M is a mass parameter of the black hole. This comes from a stress tensor, which in the sigma coordinates is equal to 1/4. The reason I'm writing it in the sigma coordinates is because the metric is flat in the sigma coordinates near infinity. So out here, the metric is flat in the sigma coordinates, meaning an inertial observer is going to see this stress tensor, okay? What is the stress tensor? Well, the interpretation is that this is the energy of Hawking radiation. This is, if this person out here is seeing some stress tensor, this is clearly not the vacuum. And the correct interpretation is that this is an eternal black hole that's Hawking radiating at some, you know, constant rate. And this is the energy of the Hawking radiation as seen by an observer out here. Ignore these R's for the moment. And the singularity is omega equal 1/4. are up here and down here. So this looks a lot like the eternal black hole we're used to. Here's the white hole with its, past singularity. Here's the black hole with its future singularity. And this is the solution. Very simple. Okay. So now I've drawn these regions R and R bar, which end at some points PO and its reflected point PO bar. I drew this because I want to now compute the entanglement entropy in the CGHS RST model on the union of R and R bar, okay? And that was done. That was done a long time ago. This is nothing other than the 2D Cft formula, okay? This is the length squared of basically the complement region. You can think about it however you want, but I like to think of it as the global state is pure. So to compute the entropy in R union R bar, I can compute the entropy across this interval that cuts across the space-time. And there's some conformal factors at these points, okay? Because it's not flat, it's conformally flat, so you need to put in these Weyl factors. And this is just a 2D Cft entanglement entropy formula for a space-time that's conformally flat. Okay, if you write this down at late times, it looks like this. Okay, there's some UV singularity, which I've just put here. It's not going to be important for what we want to talk about, but there's a linear increase in the sigma coordinates. Okay, sigma plus minus sigma minus is just some time t, and it linearly increases in time t forever. Okay, this doesn't cut off. So this is like the Hawking answer for the entropy of radiation, and this is the correct answer for CGHS or RST as sort of traditionally defined. It was traditionally defined as a theory on some fixed topology. You don't, most authors that consider these theories did not sum over topologies. And thought of that way, the correct computation for the entropy of Hawking radiation is literally Hawking's calculation. You just do quantum fields on a fixed spacetime and you compute their entropy in this way. So the theory seems to destroy information. I mean, this is the eternal black hole. We'll get to the evaporating black hole in a second, but Hawking's answer seems to be the correct answer in the model defined in this way. Okay, that's one solution. There's another solution which is even more interesting because you can write it down exactly. It's the evaporating black hole. Okay, the evaporating black hole, you can produce it by sending in a shock wave into the linear dilaton vacuum. So here, here's the usual Penrose diagram we're used to, but it's a little bit more helpful in this case to draw this diagram where I've drawn the sort of linear dilaton vacuum before the shock wave. The shock wave is made of the CFT fields. So we send in a shock wave that hits this sort of this omega equals 1/4 singular point of the linear dilaton vacuum. It's time-like here because here are the null lines. It's time-like because, as we saw, the linear dilaton vacuum had this time-like singularity or origin. But as soon as the shock wave hits it, it turns over and becomes space-like. And then there's some point where it turns around and becomes time-like again. And this is thought of as the endpoint of the evaporation. I'll come back to that in a second. I just want to write down talk about the solution for it for a second. So there's this piece again. Remember, this was the solution for omega in the linear dilaton vacuum. And now there's just some step function corresponding to the shock wave, where m is again a mass parameter. It's going to set the mass of the black hole that forms and evaporates away in this time. And the stress tensor is some delta function stress tensor corresponding to this shock wave insertion, and otherwise 0. And what's very interesting to me about the solution is you could compute, again, Hawking radiation exactly. The metric near scribe plus is flat in the sigma coordinates where I've put this tilde on sigma minus, because sigma minus is it's kind of a shifted sigma coordinate. Okay, sigma plus is defined in the usual way like this with respect to x plus, but sigma tilde minus is defined this way. It's shifted by this mass parameter m. So again, if you want to know what an observer, an inertial observer near scribe plus sees, you want to compute the stress tensor with respect to these coordinates. And you can compute that. It's trivial in this model, and you find this function. Okay. And to analyze this function a little bit, it's important that sigma tilde minus on Scri plus goes from minus infinity. It's minus infinity at I naught, that's spatial infinity, that's like the point here. And 4m represents the evaporation endpoint. That's this point. If you went up to Scri plus, that would be 4m. That's the correct answer at large mass. There are logarithmic corrections, but at large mass, that's the answer. So if we plug that here, we see that the stress tensor starts off at 0 and ramps up to 1/4. Okay, and that, what I first thought was quite impressive because I had not really seen calculations of the Hawking radiation as it turned on. So this thing starts up at 0, the black hole forms, it starts producing Hawking radiation, and the flux sort of increases until it becomes the constant value of 1/4, which remember is what we saw in the eternal black hole. It was this case was always constant because the black hole is eternal. In this case, it ramps up to 1/4. And now I just want to return to Emil's comment for a second, which is, notice this ramps up to 1/4 and stays there. I mean, okay, it's not sharp, of course, but it goes very quickly up to 1/4 and stays roughly constant for all time. In particular, it doesn't really seem to care what I called this evaporation endpoint. What seems to happen is the singularity turns time-like, yet there's still Hawking radiation. And by energy conservation, you're getting this Hawking radiation of this sort of flux, so the black hole seems to be evaporating to negative infinite mass. Okay, this, I think, was never really understood. And there was a bit of a bottom-up cheat to deal with this situation, which is that people said, okay, at this evaporation endpoint, because the metric at Scri plus seems to be flat in these shifted coordinates, I'm just going to paste on at, kind of sharply at this, along this null ray, a linear dilaton vacuum in these sort of shifted coordinates. So the global solution was considered to be linear dilaton vacuum in early times and form some black hole, some evaporation endpoint occurs, and then you paste on some new linear dilaton vacuum after that retarded time. So that was just I think an ad hoc way to deal with the solution. What the model without any sort of pasting seems to tell you is that it radiates to negative infinite mass. Now, the computations I'm going to talk about are all going to take place before this evaporation endpoint, or like very close to it, but before, so we don't really need to worry about what happens after. It's, of course, an incredibly important question how to interpret those computations, given that this is something that could be happening, and the things I'm computing don't seem to care about what happens after this endpoint. So we can return to that in the end. But for now, I'm going to ignore this, weirdness in the model. Okay. All right, well, I computed the entropy in the eternal black hole, so let's do it in the evaporating black hole. Now, I just have one asymptotic region. I pick some region R on Scri plus, some point PO here. O stands for observer. And entanglement entropy of region R, I've just written for you the answer. It's given by this, okay? There's some UV and IR divergences. The UV divergences is the usual one, the one you're familiar with in field theory. The IR divergence is the fact that this thing's at infinity. So if I consider the complement of region R, it's some region that goes all the way to Scri plus, so there's some IR divergence, which I don't care about. And the rest of the answer looks like this. And this is something that also, as you see, increases in time. And so the conclusion is both the eternal evaporating black hole in this model seem to violate unitarity. And these entanglement entropy computations, by the way, were done in a remarkable paper by Fiola, Preskel, Strominger, and Trivedi. And it's remarkable because they did all this analysis, and this was in the day where the 2D Cft entanglement entropy formulas weren't even really known. So I think they were very new. They're deriving them independently or concurrently, or maybe using some results, but all this was analyzed in great detail in this paper, and I really recommend it for people who haven't seen it. So that seems to be the conclusion. This is what you seem to get in the model. It seems to destroy information. Now, there are all these conceptual questions of whether this information destruction in 2D is really an issue, whether you can have remnants, all these sorts of things, but I'm not really going to get into that discussion. Let's just kind of proceed and try to patch up the model somehow. So let's return to the island rule entropy, which is what we want to employ. And the reason why a priori you wouldn't use the island rule entropy is that this model, as I said, is defined on a fixed topology. So, okay, that was never made infinitely clear because of the singularities and things like that. But if it's defined on a fixed topology, it's natural to expect that in the gravitational path integral, you should not include replica wormholes. If you don't include replica wormholes, it's hard to see why you would have an island rule as a way to compute the entropy. So, okay, this proposal is take this model and now sum over topologies. We don't know of a way of turning that into a UV complete model. We're just gonna think of it as like a kind of a bottom-up modification to the model. And we're also gonna assume, because I'm not gonna prove it, I'm not gonna find the replica wormhole saddles or anything. I'll provide some evidence for it if I have time. But we're going to assume that if you sum over topologies, then you get the island rule formula for the entropy of radiation, which remember looks like this. You extremize the generalized entropy. Generalized entropy is this combination. So we want to use this now as our formula for the entropy. Okay, well, we need to pick region R. In the ADS glued to flat space problem, region R lived in these flat space baths where there was no gravity. Here we're going to assume the analog of that is just scribe plus. Okay, the dilaton diverges towards scribe plus. Gravity is getting weak there. So we're going to take scribe plus to be non-dynamical. So we can put our regions R out there. That's really playing a similar role to the flat space bath. And there's a technical simplification in these models, which I find kind of interesting, although it won't be apparent when I present the answers, which is that this combination of the gravitational entropy in this model plus C over 6 rho, where rho is the conformal factor, gives you the field omega up to some irrelevant constants, gives you the field omega, which I was representing in the solutions. The C over 6 rho is just the piece of the 2D CFT entanglement entropy that came from Weil transformation, because it was log a bunch of junk over e to the minus rho, and there's a C over 6 out front. So this is from CFT entanglement entropy. So, you know, the theory sort of knows that the generalized entropy is the correct thing to consider. Generalized entropy is a gravitational plus the CFT piece, and these two pieces combine in a nice way to give you this field omega. And that technically simplifies a lot of the calculations. Okay, so now we want to revisit our examples and use this proposed modification to the rule. And there are two other papers by these sets of authors which considered similar questions of applying this island rule entropy to the CGHS model. Okay. I'm not going to really go through the calculations because it just requires, you know, doing some extremizations and plugging back in. So I'll just represent the answers. Let's do the eternal black hole. We want the entropy on R union R bar. So we want to extremize over island regions the generalized entropy. What you'll find if you do that extremization is that an island region appears that cuts from left horizon all the way to right horizon. The fact that it sits right on this horizon is due to the fact that R and R bar are sitting right on scribe plus. If you regulated them a little bit and had them be space-like regions, that kind of come inward a little bit, then this island would bleed outside of the horizon a little bit. And that would be more like what occurred in this paper, Islands Outside the Horizon, by Almheri, Mahajan, and Maldacena. But even there, if you stuck the intervals right on scribe plus, then the island region I would recede to sit right on the horizon. So that's where the island is. And the entropy due to this island takes this form. At late time. So at late times, it saturates to 2 times the black hole entropy plus this piece here. And then as usual, I put in the UV divergence. But there's this piece here, which is due to the thermal bath. Okay, there's this whole thermal bath of stuff in these left and right wedges. So usually, you know, people say that in terms of black hole, you saturate 2 times the black hole entropy, but the black hole also has a thermal bath. In the ADS case, this thermal bath is irrelevant. In the flat space case, it's infinite. So it's not irrelevant. So there's also this piece here, and that's the interpretation, is that, it should saturate at this quantity because R union R bar only has black hole plus bath amount to be entangled with. Okay, so it shouldn't exceed that. So that's sort of the answer we want. That's the answer expected by unitarity in the eternal black hole case. Okay, let's consider the evaporating black hole. Again, I'm just going to present the answer because all one needs to do once the formalism is set up is an appropriate extremization. As usual, I'm in the large mass limit, and I'm going to take the retarded time to be order the mass. So in particular, I'm in the, take the order of the mass. And the entropy of the radiation, I do a similar extremization. You'll find that an island region appears in here with the endpoint inside the horizon. What I've drawn here is the classical apparent horizon. And this curve here is basically the trajectory of the quantum extremal surface. And it's just reflected across the event horizon. Okay, that's something that seems to be true in 2D. And I think it was first noted by Pennington. So, okay, you want to minimize the two possible answers. One of them is like the Hawking saddle, where the entropy does not have an island region. One of them is like the Page saddle, where you do have an island region. And then there are these IR and UV divergences again, which I'm going to ignore. In particular, the subtracted entropy that ignores those follows the expected Page curve. It goes up, all the Hawking's calculation for a long time. There's a sharp transition because we're just doing saddle points here. And it goes down all the way to 0. And here, the Page time, which is this time here, is 4m/3. That's a third of the evaporation time. And that's simply because the black hole evaporation in this model, or in general, is not adiabatic, or it's not isentropic. If you take away some entropy from the black hole, you get more entropy in the radiation. So this point is not in the middle; it's a third of the way. Okay, so the island rule, as I was saying, doesn't seem to give us any surprises. It gives the entropies you would expect, and as has been talked about, I guess, a lot in the past few months, that's really no surprise. I mean, the design of the formula is such that you're going to get these Page curves and the answers from unitarity that you expect, because as soon as things are going to go wrong with respect to unitarity, the formula is going to tell you to include some interior region of the black hole so that the answers are consistent with unitarity. Now, I'll just comment again on this weirdness about the evaporation endpoint. It's a little troublesome that this analysis did not really care about what happened at the evaporation endpoint. So in particular, if the model really had black holes that radiated to negative infinite mass, you might think that you shouldn't get a unitary Page curve in such a model. So I don't really have much to say about that. I mean, Tom Banks has written about that a little bit and suggested that maybe from the replicable wormhole point of view, if you go to try and derive these replicable wormholes, that you'll find that in a model where that happens and thing radiates negative infinite mass, you just don't have these wormhole saddles that give you the island rule entropy. And in better models where that doesn't happen and you do have some vacuum after the black hole evaporates, you would have replicable wormhole saddles. So I don't think that's really known. Here we're just taking the island rule by fiat and seeing what it gives us. Okay, I wanted to motivate a little bit. I mean, I'm not going to derive the replicable wormhole saddles, but I wanted to motivate a little bit why it's a reasonable thing to do. And there's basically a local argument for QES, here means quantum extremal surface. There's a local argument for this prescription. And I'll cast it in the context of a general dilaton gravity. As I said, CGHS or RST can be written in this way, where this potential is just a cosmological, it's just a constant. But you can do it more generally. So let's say that this is your action. CFT, as usual, is just minimally coupled to the metric and not coupled to the dilaton. And let's analyze this in a particular limit. So we want to work in light cone gauge, in conformal gauge. And we want to place a defect. The defect is going to represent the boundary of the island region I. Okay, so it's where the quantum extremal surface is supposed to go. We want to place that at z equals 0. So we're just picking coordinates where it's set to z equals 0. And we want to work locally near z equals 0. And since we just want to compute the entanglement, we want to work for n near 1. Okay. I won't do this in the Kruskal gauge from before where I just had this field omega. Well, I'm doing a general sort of theory. So I'll work with the phi and rho fields, which I said phi is captures the dilaton and rho captures the full metric because I'm in this gauge. And I want to expand them for n near 1 in this way. Okay. And as usual, I have the metric provided by the CFT. And here I'm just writing the metric in flat space, meaning without this e to the 2 rho. So it's missing some conformal anomaly piece. Expand them all around n equals 1. And as I was saying before, in response to a question, the replica manifold has to be smooth. The gravitational part has to be smooth. There are these regions R in the non-dynamical space-time, which are glued across the sheets, and you can have singularities there. But any sort of replica wormhole region should be smooth. And what that means is that in the quotient manifold, it's going to be singular. But the smoothness on the replica manifold tells you what this conformal factor looks like. You can just plug this in the metric dw bar and find that delta rho is this. And there's one more thing we need, which is this equation for delta t, which comes from the conformal word identity and tells you that the flat space entropy, meaning the entropy without the e to the rho conformal factors inside the log, appears here. Here we've used the scaling dimension of these twist operators. And the barred equation, okay? Same thing with just bars on the t's and z's. And now what we want to do is we just want to solve the constraint equation. So we expand the dilaton, this delta phi, in a series, and we want to assume replica symmetry. So we assume replica symmetry, meaning we only have combinations like ZZ bar. And if you solve the singular term of the constraint equations, which are just the equations of motion for GZZ and GZ bar Z bar, you actually find that to solve those singular terms, these are just the simple pole terms actually in the equation, you find that this has to be true, that the derivative of the gravitational entropy plus the CFT entropy is 0. Okay, and this is just the QES condition. This is the thing that tells you to extremize the generalized entropy. So this is an argument for the quantum extremal surface prescription. I mean, it's not a complete argument because it's sort of assuming that there exists the quantum extremal surface somewhere, and then it tells you where it goes. What you ideally want to do is really construct the replica manifolds at finite n, which we haven't done. And something to mention is, from the replica point of view, from the island point of view, it's obvious that this stuff is going to work given the structure of the formula. From the replica point of view, it's not so obvious. I mean, there are some deeper worries, which is this, in the evaporating black hole case, this naked singularity that appears in late time and how to construct replica wormholes. But then there's some slightly more naive worries, which are like the following. You could have expected that in the ADS2 model, you can have these replica wormholes, which are manifolds of non-trivial topology, because it's easy to create manifolds of non-trivial topology on hyperbolic space. Okay, famously in 2 dimensions in the classification of manifolds, that's how you go to higher genus. You just work on hyperbolic space. As soon as you increase the genus, and those are the manifolds you could write down. Whereas in the CGHS or RST model, if they're actually equivalent to flat space JT has R equals 0. And we're used to thinking of totally flat manifolds as not ones in which you can, have metrics for higher genus surfaces that are flat. So you might worry, what are these replica wormholes you're talking about? Do they even exist? I mean, this complaint is a little bit more naive because there are these sort of singular points out at infinity that I was talking about. And those singular points allow you to, don't disallow the possibility of constructing these higher genus flat manifolds that we're talking about. But anyway, that is just a tangent. Let me see. Okay, how much time do I have? I don't know exactly when I started.
I think we started like 5 minutes later.
Okay, so I have like 8 minutes.
Yeah, I think so. Yeah.
Okay, let me see. I mean, maybe I'll flash this real quickly and move on. You can ask, what does this mean? The fact that there are these island regions, and the usual interpretation is that using the ideas of these authors combined with there's some evidence for it, but it's mostly a hypothesis, I think known as entanglement wedge reconstruction. What this seems to tell you is that this island region is encoded in some non-trivial way in the radiation region. Okay, what that means is if you have some operator you want to do something inside this black hole, there's some operator you could construct in the radiation region, which does the same thing as long as you restrict to an appropriate code subspace. So this is an interesting thing to try and pursue and understand, and there's still papers appearing about entanglement wedge reconstruction. In the context of islands and black holes, the two approaches that have been considered, one is by using this tool known as the PETS map, and this appeared in the Stanford paper. And then there's also an approach using modular flow, which appeared by Yiming Chen, and both of them seem to be ways that they seem different, but maybe they're related in how to get the information out from this region I. But I just want to flash this as a connection to what this means. And in flat space, it's quite interesting because it seems to suggest an encoding on Scri+. I mean, this is something that people have often talked about, how to understand holography for flat space. This isn't really holography. This is holography in the sense of entanglement wedge reconstruction. The state here is encoded in a state here. But hopefully down the line, it gives some sort of clue for how to think about encoding stuff on Scri+. Okay. Well, okay, I don't know how much, I guess I'll just flash this because I wanted to talk about some upcoming stuff, which I think is kind of exciting. It's a totally different gear, which is, you know, how to, if you wanted to, you know, this island phenomenon seems a little bit general. I mean, there's situations where islands appear, but it seems to be a statement you can make in general whenever you have field theory coupled to gravity. And you might wonder, how do we guide our search for these islands? Like if someone just handed you a space-time and you wanted to see if there are island regions, disconnected island regions, how would you do that? So what are some consistency conditions for islands so we can understand really when they appear? So far, they've appeared mostly in the black hole context, right? So we'd like to see if they're more general than that. And there's some pretty simple consistency conditions you could write down. The first necessary condition is the one about the island region dominating, right? That you want the generalized entropy with island to be less than the generalized entropy without an island. Okay, that's pretty obvious necessary condition. But we want to massage this into a condition just on the region I, because that's the thing that's helpful. That's what you would use if someone handed you a space-time and said, are there islands here? You'd want to just think about the island region I, because the region R could be anywhere. It could be a disconnected space-time or same space-time. So we want to massage this into a condition just for I. So we rearrange it a little bit. We add the matter entropy of I to both sides and move terms over. And then the Iraqi-Lieb inequality applied to this right-hand side tells us that this left-hand side is positive and gives us this. Okay, I pulled a fast one here in that I put this little squiggly and I put a hat on the S, because this argument is naive. There are infinities in this equation that don't cancel out. So in particular, the left-hand side is not the generalized entropy, so it's not a finite quantity. If you're more careful about the infinity, you know, this inequality would just tell you that infinity is greater than 0 or greater than finite. But if you're more careful, you can regulate this in an appropriate way. And the thing you get is morally just that the finite piece of the matter entropy should be roughly greater than A over 4G. Okay, so it tells you the intuitive thing that people often understood about islands, which is that anytime the matter entropy gets large and you can cut the cost in the generalized entropy by including an island region, you should do it. Okay, again, to make that precise requires being careful about the infinities, but that's one necessary condition. There's another necessary condition, which is just that extremality condition. So the extremality condition tells you that the derivative of the generalized entropy has to be 0. So this is independent of whether or not this island solution dominates. It's just that it's extremal. This lambda plus is like imagine this is a 2D problem, and it's like a null outgoing derivative, okay? And you can rewrite this in this way. So I've expanded out the generalized entropy, and then I've added and subtracted, again, S matter I from this expression. And I've also added S matter R, because this derivative is with respect to the endpoint of the island. So it vanishes when acting on this. And you can see that this is just negative the mutual information. So in particular, monotonicity of mutual information tells you that the outgoing null derivative of the generalized entropy of I is non-negative. And for the inward going null derivative, it's non-positive. So this is encapsulated by this pair of inequalities here, which defines a quantum normal region. Remember, classical normal regions are regions that are not trapped or anti-trapped. So, things that outgoing things go out and ingoing things go in. Whereas, inside of a black hole, an outgoing thing actually goes in. I mean, because it can't escape the black hole. So it's a classically trapped region. A quantum trapped or anti-trapped region is, instead of thinking about the transverse area and what that does, you think about the generalized entropy. So quantum normal means it's not quantum trapped or quantum anti-trapped. So you get this inequalities for the region I. Okay, so here's the pair of inequalities. What's, again, nice about these is it makes no reference to region R. Okay, so you can just analyze a space-time on its own without thinking about where you're going to put region R, and they're necessary conditions. In particular, you can use them to rule out whether a space-time can have an island region, independent of what region R is chosen. Okay, so the quantum extremal surface, the boundary of the island region I, has to be in the intersection of these two regions because they're necessary conditions. And I'll just flash an interesting space-time where this non-trivially constrains where the island region has to be. This is a crunching cosmology. So there's a big bang, it grows, and then it turns around and crunches. So this is well, you can have this in various cases. A case where people often think about space-times like this is in the context of Coleman-de-Lucia bubble nucleation, where you bubble nucleate a bubble of negative cosmological constant, which tends to take over at late time and causes space-time to crunch. But anyway, if you look at this inequality here, to compute the Bekenstein violating region, you find this yellow strip out here. Okay, that kind of makes sense. You need to take very large spatial regions so the matter entropy overcomes the gravitational entropy. The state considered here is thermal. Okay, that's important. So if you get large enough, the thermal state's volume entropy will beat its area entropy. And the quantum normal region is this blue slice here. And blue and yellow overlap to green. And so any endpoint of the island has to be in this narrow strip up here. And in fact, in particular examples, you can construct a region R with an island region I whose endpoint sits in this green region. Okay, that was a wild tangent to flat space because this is not flat space. But these conditions are also interesting to check in the black hole cases. You can go back to the RST model and check anytime an island appeared, these things were true. Okay, I mean, they had to be true if they were derived correctly. But it's interesting to check them and kind of see often how narrow the window was of where something could have appeared. Okay, I'll summarize and then I'll take questions. So the premise, the backdrop in my mind for these sorts of questions is the replicable wormhole perspective, which gives you a derivation of things like the island rule. And it leads to a unitary page curve in black hole evaporation. As we talked about, it's almost too good. It can give you unitary page curves, in these situations where the black hole seems to radiate to negative infinite mass. At least the island formula does. It's unclear if you can derive it from a replicable wormhole point of view, but that's an interesting thing to explore. This mechanism seems to be, in general, I mean, these were found to be saddles in like JT gravity coupled to ADS for n near 1. But, as off-shell configurations, they should presumably exist in any number of dimensions for generic theories of gravity. So it seems somewhat general. And the bulk of this talk, we're talking about the CJHS or RST models. They, as understood, seem to destroy information. You might want to modify these models by summing over topology, and the proposal was that that would lead to a unitary page curve. It would be nice to understand this sum over topology better and how to define the model in that context, but it's not currently understood. And the last point I ended with is that these there are consistency conditions you could write down for islands, and that can help you find islands in more general spacetimes, because they only care about the region I. So you can analyze a spacetime without setting up some region R whose entropy you want to compute, etc. All right, I'll stop there and take any questions. Thanks.
Okay, thank you very much. We already have one question, which was waiting from Orestes. So the question is, in compact spacetimes like ADS, fluctuations should not dissipate, and thus should be no information loss. Is this somehow connected with the island argument?
I didn't quite understand the issue of there not, I didn't quite understand the argument for there not being information loss. If Orestes wants, you can unmute and clarify. I think there was always the not knowing ADS CFT, there was always the possibility of information loss in the theory, in the sense of the old, maybe GR-ish perspective, which is that, the black hole, once it sort of evaporates away, just kind of like tears off into like a little baby universe that traps its information in there like a remnant, and you can't access it in any way from the outside. The current island picture, as understood, it is very closely related to that, except the statement seems to be that by doing complex enough operation on the radiation, you can access the stuff in that little baby universe. But I don't know of an argument a priori that there should not be information loss, unless, of course, you assume ADS CFT in its strong form.
Hi. Yeah, I think the argument assumes full ADS CFT with quantum fluctuations and everything. So yes, if you do classical gravity, you will lose information, but if in principle you were taking into account everything, there shouldn't be any information loss because you have a fluctuation in a compact spacetime, so it shouldn't dissipate. So the oscillatory behavior should always be there, even if you have a black hole and, let's say, not a microstate or something else that people construct to get this oscillatory behavior in the two-point function.
Yeah, I don't know that you need an ADS. I think as soon as you assume ADS CFT in its complete form, then you can just say that the CFT is unitary, so you can't possibly have information loss.
Yeah. I think that's the argument. So right. Is the island argument revealing something from that? I guess that's my question.
Oh, the original island argument from the point of view as derived from holography was just it sort of gave you a more bulk way to think about how the entropy of the radiation goes down to zero, because this wasn't a computation that could be done before. We knew that the entropy had to go down to zero. There wasn't a way to see how to do it. And then the gravitational path integral point of view seemed to tell you more generally, even beyond ADS, how to expect such an answer.
Okay.
So, like I said, in the flat space case, I didn't, we had nobody's provided a complete derivation of that.
Mm-hmm.
But the general picture seems like it should be true, and I provided at least some evidence that it would give you something like an island formula, which would return the entropy back down to zero. But it's doing semi-classical Euclidean gravity, so there's still assumptions about the UV theory being put in. For example, is the UV theory such that you should include these replicable wormholes and get the island rule entropy? So in the work that I was talking about here, we're assuming the answer to that was yes, that there is some model like CGHS or RST, that UV completes to something such as the island rule entropy gives you the right answer. So in that sense, without the UV model, we're still kind of swinging in the dark a little bit.
Okay, thank you. Yeah.
Yeah.
We have another question from Baiba, which says, do you think that the island prescription makes it possible to reconstruct the bulk past the quantum extremal surface? If so, can we actually recover information from the black hole by means of the Haydn-Preskel protocol?
I assume past the quantum extremal surface means in the island region, in which case, yes, I think that is the perspective entanglement wedge reconstruction. If you believe in entanglement wedge reconstruction, then that's what it says, that if you restrict to a code subspace, that you can have operators act on the radiation region R and do for you whatever an operator in the island region I would do. And the Haydn-Preskel protocol, I think, yeah, that was, I mean, in the original, in the first papers by Almeri, Marolf, Maxfield, and Pennington, this was sort of analyzed, and they saw that with these island regions I, they realized some form of the Haydn-Preskel protocol. I didn't talk about it here, but in the RST model, there's a similar sort of thing. I mean, there's again this annoyance of dealing with this infinite asymptotic flat region. But if you appropriately define things and regulate things, then you also seem to get the Haydn-Preskel protocol from the island prescription.
Oh, I think there's a question by Emil.
Yeah. So in the CGHS model, I mean, it's simple enough that one can just compute the outgoing state. And it consists, not surprisingly, of a bunch of uncorrelated Hawking quanta, which are entangled with partners in the region behind the horizon. And so, in particular, it's uncorrelated with the infalling radiation. I mean, it's just basically the result of Hawking's calculation. And so it's not clear to me how summing over topologies is going to help you. It seems like just opening a completely different can of worms. I mean, it's basically like saying, if I want to think of the universe as some kind of macroscopic string, which is basically what it is. If I wanted to view the model in terms of string theory, I would say, okay, I'm looking at some solution of string theory in some supercritical dimension where the number of spatial coordinates is enormous. And okay, and then you should think of your phi and rho as being like a pair of light cone coordinates. Introducing topology change seems like a can of worms you don't want to open, because you're just looking at bosonic string theory in the supercritical dimension. And as soon as you allow the world sheet to start changing topology, all hell is going to break loose because there's a tachyon instability. So it doesn't seem like, in a Lorentzian point of view, topology change is going to help the problem. It's just going to make it worse. And that's so like comment one. And then comment two is that, thinking of it as a string theory model where you've got one macroscopic string and a whole bunch of little baby strings that are being ripped away from it. That usually obeys the rules of causality, because the Virasoro conditions of world sheet string theory are just the projection of the field space causality onto the world sheet. So it's not clear to me how, decorating that with topology change is going to change the fact that the information behind the horizon is causally disconnected from the radiation going out to infinity. So I wonder if you have some comments about that.
Well, for the first comment, I mean, I definitely agree. Summing over topology is opening a can of worms. I view whether that's the right thing to do or not as a question of whether this model, I mean, this model was sort of considered a toy model, but let's focus on it for a second because it's the one that for 2D asymptotic flat space has been studied the most. I mean, it was never derived in a top-down way. I mean, it seems closely related to the theory on NS5 brains, like the black holes have a Hagedorn scaling, etc. But it was never derived in a top-down way, and it's possible that it just doesn't exist in string theory. In which case, I would say who knows what it is? It's probably a sick theory. The hope is that it does exist, either this model or some related model that's asymptotically flat does exist in string theory. And then I view it as somewhat natural to include the sum over topologies. Again, without access to the UV complete model, I don't really know, but it's natural to expect a sum over topologies, and it does something good for you. At least it seems like it should do something good for you, like it did in the ADS case, which is give you a unitary page curve. Again, in 2D, I mentioned this briefly, information loss doesn't seem like it would, other alternatives like remnants and stuff don't seem as problematic as they would be in higher dimensions. But the fact that you get a unitary page curve, I view as like as a pro for including these topologies. But it's hard to say anything without having the UV complete model. And like I said, with CGH and RST, I think it's an important point to remember that it was never derived in a top-down way. So maybe it doesn't exist. I think I've forgotten the second comment. Oh,
the second comment, yeah, was just that the information is the information of what you sent in and of the entangled partners of the radiation quanta doesn't seem to have any hope of, well, you sort of declared that the stuff behind the horizon is, should be lumped in with the radiation. And it doesn't seem to have any hope of getting back together. So this ideas of Petz maps and so on and so forth.
Yeah.
I mean, the model has an explicit Hamiltonian, which seems to be factorized between the asymptotic radiation, the stuff behind the horizon, and including topology change processes doesn't seem to have any hope of, uniting those two disconnected parts of space-time, because they really are spatially disconnected, not just in 2 dimensions, but in the field space dynamics. So if we're going to appeal to topology change, the point is that those 2 bits of information are acausal in the field space metric. And so as long as we're just appealing to processes like changing topologies, you're not going to get things to travel faster than the speed of light. So if you split off some baby universe, that baby universe is not going to travel faster than light in the field space metric, as long as you're using the standard rules of topology change that you get out of out of thinking about world sheets propagating around in some embedding space. So
yeah,
it seemed like there's some way that the things could somehow communicate with one another and magically restore information.
Yeah, I haven't thought about it from the point of view of causality in the field space metric. I mean, my perspective is maybe this somewhat conventional one for people who have been working on these things, which is that, okay, I don't know if it's conventional or not, but it's that, you know, causality in this situation is a rather subtle concept, and well, okay, yeah, maybe let me bring up a let me maybe bring up an analogy. If you think of these like holographic realizations of these islands where you put brains through the bulk, like what Almheri Majam Al-Zhanijau originally did, and what Myers et al. Have been doing. In those situations, there's a possibility for something that I like to call causal islands, which is just this old thing that if you go into the bulk in ADS, then the Galois theorem does not really ensure for you anymore that you can't have causal shortcuts through the bulk. You can go through the bulk and get to somewhere faster than had you gone through the boundary. And as soon as you put brains in the bulk, then you are roughly in that situation where you're not all the way out to the ADS boundary. And then causality seems a little bit strange. Just by analyzing the usual setup, you would think these things are causally disconnected, but actually there is a way through the bulk in which they are causally connected. So that's kind of tangential, but I want to bring that up as, in my mind, a subtlety of trying to like deduce what the causal relationships are once you have fluctuating gravity. And then independent of that, maybe I'll give the more conventional perspective that people often have, which I'm sure you know, is that, you know, if you don't think about it in the field space metric, which maybe is what you want to emphasize, if you do these sorts of complex operations, then you need to understand what those complex operations are doing to the space-time. So as you know, the PETSMAP picture is some picture of wormholes being created, which give you some connection to things you otherwise wouldn't have a connection to. I mean, all this stuff is very vague. I would love to understand it better. Mm-hmm. Maybe the perspective you're offering is one way to do that, but it's not clear to me that these things are really causally disconnected in the theory of quantum gravity.
Okay, I think I was just making the comment that you're probably doing something different than the way one would conventionally approach topology change in 2 dimensions, which is, you know, our one example of how we know how to do that is worldsheet string theory. And so you have to be doing something quite different than that.
Yeah, that may be. I haven't thought about it too carefully from that point of view. That may be.
Sorry, just in view of time, and since the discussion might continue for a while, I suggest we stop here, we thank Edgar, and then we continue with the discussion session.
All right.
Okay.
Thanks, everybody.
Thank you very much.